Let's have a look at some more examples of the Taylor series using two variables. Here we have another example where we're asked to go as far as the second order terms. G of x and y is x over 1 plus x plus y. We're expanding around the point x is 2, y is 1. And then we're asked to evaluate at a point 1.8, 1.1, that is relatively close to 2, 1. Let's compare with the exact value. So here, we're being asked to expand around the point 2, 1. So that gives us that the value of a is 2, the value of b is equal to 1. Now our function, g of x and y, we can write it in a form that's slightly easier to differentiate. We have x times 1 plus x plus y to the power minus 1. So here's g of x and y. G of 2, 1. X is 2. 1 plus x plus y at 2, 1. 1 plus 2 plus 1. That will be 4. So we'll have 2 over 4, which is equal to 1/2. The derivative with respect to x, firstly at the general point, product rule, will have 1 times 1 plus x plus y to the power minus 1 plus x times minus 1 times 1 plus x plus y to the power minus 2. The derivative with respect to x of the bracket is 1. So what we have here is 1 plus x plus y to the power minus 1 minus x times 1 plus x plus y to the power minus 2. And then that means that gx at the point 2, 1. Remember, this bracket is equal to 4. So we'll have 1 over 4 minus 2 over 16. So we have 1/8. The derivative gy, that is the derivative with respect to y, well, y only occurs in this part here. So we'll have x times minus 1 times 1 plus x plus y to the power minus 2. So that comes to minus x times 1 plus x plus y to the power minus 2. And gy at the point 2, 1 will be minus 2 times 1 over 16. That's minus 1 over 8. Now we go towards the second derivatives. The second derivative, gxx at x and y, we differentiate gx. So we'll have minus 1 times 1 plus x plus y to the power minus 2. And then from the product rule here, minus another 1 of those same terms, hence the 2 here, minus x times minus 2, that's plus 2x, times 1 plus x plus y to the power minus 3. And when we evaluate this at the point 2, 1, we have minus 2 over 2 squared plus 2 times 2 over 2 cubed. So we have minus an eighth plus a 16th, we get minus 1 over 16. The mixed second derivative, we can differentiate with respect to x, with respect to y here, or differentiate gy with respect to x if we try the latter. So gxy as a function of x and y. Differentiating with respect to x, we have minus 1 times the bracket here. So minus 1 plus x plus y to the power minus 2. And then we have minus x times minus 2, that is plus 2x times 1 plus x plus y to the power minus 3. And again, let's evaluate this at the point 2, 1. Minus 1 over 16 plus 2 times 2 over 4 cubed minus a 16th plus a 16th. This term comes to 0. And then finally, gyy take gy and differentiate with respect to y. Y only occurs in one place, so minus x times minus 2, 2x times 1 plus x plus y to the power minus 3. And when we evaluate this at the point 2, 1, we have 4 over 4 cubed. That is 1 over 16. Here we have our general second order Taylor series for g of x and y evaluated around g of a and b. Here a is equal to 2, b is equal to 1, so we will have powers of x minus 2 and y minus 1. So it starts off 1/2, and 1 over factorial is 1, so we have x minus 2 times 1/8. We have y minus 1 times minus 1/8. So that's the first order terms. 1/2 x minus 2 all squared times minus 1 over 16 plus 2 times x minus 2 times y minus 1 times 0 plus y minus 1 all squared times 1 over 16. And there will be third order terms and higher order terms as well. So now, tidying this up slightly, we have 1/2 plus 1/8 of x minus 2 minus 1/8 of y minus 1 minus 1 over 32 times x minus 2 all squared plus 1 over 32 times y minus 1 all squared. So now our task is to estimate, using the function, g of 1.8 and 1.1. Well, if we set x equal to 1.8 and y is equal to 1.1, that gives us that x minus 2 would equal minus 0.2, y minus 1 would equal 0.1. Let's use the series to estimate things. So for the 0 order, we just have 1/2. For the 0 order, it gives a 1/2 everywhere. Probably no real reason to assume that is specifically accurate, but it's our starting point. The first order, that's the top line here. G of 1.8 and 1.1 is approximately equal to 1/2 plus 1/8 of minus 0.2 minus 1/8 of 0.1. And when we work this out, 0.4625. Well, is it any good, our first order approximation? Let's work out the exact value. So let's use the calculator here. X over 1 plus x plus y, where x is 1.8, y is 1.1. So 1.8 divided by, remember the brackets, 1 plus 1.8 plus 1.1. 0.4615. 0.4615. So to 4 decimal places, we're out slightly in the 3rd decimal place. Let's see what happens when we go to the 2nd order approximation. So g of 1.8, 1.1, we will have our previous answer here, and then we'll need to add in the 2nd order terms. So we'll have 0.4625 minus 1 over 32 times minus 0.2 all squared. So 1 over 32 times minus 0.2 all squared is 0.04. And then we have plus 1 over 32, and we have 0.1 squared. That's 0.01. When we work this out to 4 decimal places, 0.4616. So you can see, going to the 2nd order, we've now confirmed the 3rd decimal place. We're only 1 out in the 4th decimal place. So, using the 2 orders of the Taylor series, we do seem to have a quite reasonable approximation. Here we are told that for the function z is equal to 2 plus sine x over 4 plus y squared, the 2nd order Taylor series around the origin 0, 0 is z2 given by 1/2 plus a quarter of x minus an eighth of y squared. We're asked to compare curves of constant z and z2. This will show how good, or perhaps how poor, the approximation is. And then we're actually asked to repeat for the fourth order series, where we have the second order terms, third order terms, and indeed we have a fourth order term. Again, let's see how good, or perhaps how poor, that approximation is. For an area close to the origin, we can see here solid curves representing our original function z for 0.4, 0.5 and 0.6, whereas in dashed we have the corresponding curves for the second order approximation, that is z2, again for the same values of the function. We see those contours. Now for 0.5, the contour which passes through the origin, at this scale the approximation lies sufficiently close to the function that we can't see any difference between them, whereas we see minor discrepancies for 0.4 on the left and 0.6 on the right. Moving out a little bit further, we can see that yes, the second order approximation does move slightly away from the actual function. When we get further away from the origin, the others too have larger discrepancies the further away from the origin we get. Moving further away still, we see some quite large discrepancies, say between the orange contour for the function represented here, whereas the approximation to two orders gives a totally different type of behaviour. Then further out still, we see that while the function itself has a fairly complicated structure, the second order approximation is merely a series of parabolae. But we do see that near the origin, those parabolae do approximate the function really quite well. So it would seem the second order approximation does a good job of approximating the function near to the origin, but a significantly poorer job when we go further from the origin. We can represent the fourth order series and its contours by shorter dashed lines. Now when we just look at this small area near the origin, we don't see any of the fourth order ones because they lie so close to the curves for the function. But moving out slightly, we do see that yes, look at this purple one for 0.6 for example, about here the fourth order one does diverge slightly from the actual function in solid, and the same thing can be said for some of the other lines that we have here. We will notice, for example, if we look at the brown contour here representing 0.7, that whereas the second order series is slightly removed from the actual function, the fourth order series does a much better job of approximating the function. But it too breaks down when we go to higher distances from the origin. For example, if we were to follow the green curve for 0.4 around, the actual function goes in one particular direction, whereas the fourth order approximation just takes a totally different path. So we conclude that the fourth order approximation near the origin does an even better job of approximating the function than the second order approximation does. But once we go further from the origin, the fourth order, just like the second order, becomes less useful. Indeed, when we zoom out further, we can see that just like the second order approximation giving a series of parabolae, the fourth order series also gives a behaviour that seems nothing like the behaviour of the underlying function. So both are excellent near the origin, the fourth order more so than the second order, but they both break down as we go to higher distances from the origin. So a Taylor series in 2 dimensions, a good approximation near where we're approximating around, perhaps less good too far away from the point around which we have carried out our approximation.